Hello, welcome to the fifth of our Nuclear Masterclass webinars. I'm Dr. Charles Barton. I'm a nuclear physicist working at the University of York. And so let's go to this evening's event. And tonight we're joined by Dr. Yulia Furlatova, who's a staff scientist at the Jefferson Lab in America, where she works on the Electron-Ion Collider project. This evening, she'll be talking us through this exciting project and how it may allow us to answer key questions on the structure of protons, the behavior of quarks and gluons, and how matter behaves at extreme densities.
Thank you very much for the introduction, and thank you very much for your invitation. I hope you can see everything and hear everything well. So let me start with a few thank you notes. So my slides were really inspired by the lectures of various peoples, and I really would like to thank ESC project and DOE of the United States for giving me an opportunity to enter this webinar, and also the EPIC collaboration. So today I will skip the slides about me, so you already had an introduction. And today I'm going to speak about the Electron-Ion Collider, but I will want to start with really high-level questions, which we are scientists trying to address during our career science. And then I will go to the deeper into the specific questions which Electron-Ion Collider we're going to address, and how the accelerator design looked like, and why we need that, and what kind of the experimental setup and detectors we are planning to build. And I will end up with a conclusion. So let's start with the high-level goals for us as a scientist. And so number one question which we have is, where did we come from? So when I was a student like you, I always dreamed about galaxies, stars, and but for me it was really important what actually happened in the first seconds of our universe. And I was curious to understand how I can go back and check what happened at that period of time. But then when I started to study in my college, so I realized that we can address some of those points, some of those questions using the particle accelerator facilities. And this is exactly why I ended up in particle physics world. So the second question what we have is, what is the universe is really made of? We know that our observable matter is about 40%. So this is what the tiny little bit, this is what actually what telescope can see. But the other, 23 or 73%, sorry, the dark matter or dark energy. But we really would like to go and see what are the really tiny little pieces and the building blocks of the universe. And the third question what we have is what actually holds us together. What kind of forces we have which keep us all together. We know all about the gravitational force. I do not have to explain this. We know about electromagnetic force for the centuries already, so this is also very known. And there are two other forces, strong and a weak force, and the strong relates to how quarks are glued together inside the atom, inside the proton. And the weak forces, this is the force which responsible for decay, for example, of the neutrons to the protons and so on. But if you look at the scales, you can see, so if the strong force is a scale of 1, so you can immediately see that the other forces, such as the gravitational force, is really, really weak. And this is why we still didn't discover the carrier of this force, even so that we can feel it every day. So you all already know about the periodic table, and this is exactly what particle physicists are trying to build, how the fundamental particles are forming the periodic table of particles. In similar way, what the the periodic table of the elements, right, from the Dmitry Mendeleev. But in this case, this is a similar way. We know what are the tiny little pieces which we know the elementary, do not have the internal structure. This is to our nowadays knowledge. And we are trying to see how they form and what kind of periodic structure in this table could be seen. And what you can see here that we have our force carriers, gluons, photons, and carriers of the weak force. We call them bosons, so they have the spin 0, 1, and the Higgs, very famous Higgs, is also sitting here. And we also have another tiny little pieces, elementary particles, which making the matter. So we call them fermions. So there's quarks and the leptons. And as you can see, there is a 3 generation, there is a mass hierarchy. Every time we go to the next generation, the mass of this tiny little pieces are getting higher. And what is really interesting that the quarks, which you can see over here, they have a fractional charge. And by the way, I saw some really cool quote sometimes in, I think it was in Facebook or something. There was saying, what are the definition of the particle physicists? So particle physicists, because we are all made of the quarks and the leptons, the definition was that this is the ability of quarks and leptons to think about quarks and leptons, right? So we are fermions. So about the fractional charge, there is still no direct observation of the fractional charge or any isolated quark. So all quarks, this is what we know, they are forming more complex structures. We call them hadrons. So 3 quarks are forming state which we call the baryons, and quark-antiquark pairs, they're forming some structure which we call mesons. So this so the most famous hadrons are protons and neutrons. So proton is made of the UUD quark, and neutrons is made of the DD and U quark. So, and but of course, right now, in the half of a century, we observed more than 200 particles, baryons or mesons, and they're all listed in this, data particle group book. So you can click here and go and, read all the properties of those hadrons. But we are also trying to build what is the periodic table of those hadrons, right? How they are, what if you, for example, plot them versus the charge or number of U or S quarks, how they are formed together. If you add another quark like charm quark, so it's becoming already multidimensional. And this is a still open question, like how the periodic table of all hadrons, baryons, or mesons look like. So this will be a question for you to address as well. So already for the half of the century, we know that we made of the quarks and the gluons, which hold the quarks together, right? And those small pieces are actually making up to like 90% of the mass in the visible universe. But up to now, we were not able to see those tiny little species. Why? Because we didn't have the instrumentary, right? If you look at the scale, so for example, looking at the crystals, you can look with magnifying glasses. If you go down to the atom, you need some sophisticated microscopes. But in order to get into the quarks and the gluons, you really need to go into the very small scale. So if you comparing to the atom, for example, if we take the size of the atom as a 1, we have to go down by the 100 million times smaller scale in order to really be able to spot the quarks and gluons. And with the help of the particle accelerator facilities, we exactly can, nowadays, we can probe this femto world. I don't know if you're familiar with the scale. So the scale of the like proton or the quark sizes will be at the order of 10 to the minus 15. So for me, meters. So it's for me, it's really amazing how our technology is really allowing us to look at this deep structure. So another question which we are trying to address is what is the how the proton looks like. And so we know that it consists of 3 quarks, but how they are distributed inside, how they interact inside the proton. What if any modification in the structure of the proton, if, for example, we compare the proton with, I don't know, the protons inside the atom of the iron, for example, or heavy, like uranium or so on. And how can we measure actually this structure of the proton? Yeah. And I will just briefly introduce the way how we are measuring this. And you're probably already familiar with the Rutherford experiments. And Rutherford experiments in, I don't know, like 100 years ago, what he did. So he took the alpha particles and he shot with alpha particles with the gold foils. And he measured, he had this, the detecting foils all around the world. So what was the expectation? That if there will be no dense core, then all the alpha particles will be sort of absorbed in a front face of this beam. But what he observed that those alpha particles are really getting some kicks, right? And that was due to the observation of the dense core inside the atom. Similar way, what we are doing with the proton. But instead of the alpha particles, we are taking the high density electron beam and we shoot on the proton. And similar way, we are looking at the scattering angles of the electrons, and this is what gives us the possibility to study the structure inside the proton. And the first experiment was done in early 70s at Stanford facility, and what was observed. So this is really a cool picture. I try to draw you so that you can understand what we are measuring. Imagine that your proton has no structure or has a single quark or no structure at all. In this case, when you check what will be the fraction of this quark momentum inside the proton, and you compare it to the momentum of your proton, and you measure the distribution, and in order to get this property, you can actually just measure the very simple the energy and the scattering angle of your scattered electron. And in this case, if there is no structure, and you plot this as a function of x, you immediately see that the distribution is around 1. Because this quark will carry the entire momentum of the proton, right? And if there is a 3 quarks, of course, this momentum will be distributed and shared between those 3 quarks. That means for the single quark, it will be, because we are scattering of the single quark, this will be 1/3. If the quarks are interacting inside a proton, so of course, instead of this peak or the delta function, you will see some distribution. And if there is a production of other pairs, quark antiquark pairs, what we call the C quarks, in this case, you will see that this distribution is getting some tails in a low X region. Just because I'm going to the next slide to use the different abbreviations for the mass. So this is you can check what are the giga-electron volts. They call the GeV or MeV, and how this links to the mass of the various particles. Yeah. So for you, it's really cool to see that mass of the electrons, for example, is 10 to the minus 1 kilos. And this is really cool to compare. So this proton structure was measured, and this is exactly the distribution which I previously showed. That was measured at HERA, and this is exactly what we are doing at Jefferson Lab with our CBAF accelerator. And I'm going to show you what are our current understanding of the proton structure is. But before doing that, I want to dive into the questions about the Electron-Ion Collider. And the Electron-Ion Collider, we started to think about this, I don't know, 20 years ago. And all those papers, it was a collective work of the scientists and experimentalists and theoreticians to put together all the science questions which we still need to address. And one of the main questions was like how the distributions of the quarks and gluons looks inside the proton, and especially at the different scale. So I told you about this X distribution, but if you compare, let me go back. If you look at the valence quark distribution, you immediately see that they are follow the distribution which we predicted, but the gluons, and this you can see this form is showing the scale factor. That means we have a lot of gluons, and the better more we go with the energy, more gluons we observe, or more granularity, or we are checking the smallest particles of the universe, the more gluons we are seeing. And this is like a popcorn machine, right? So we are trying to go to the tiny little pieces and measure the energy momenta, but we see that the proton is becoming as a soup of the gluons, and we almost cannot see any quarks around them. But this cannot really happen forever. So at some point, gluons have to interact with each other, and that's what we call the recombination or saturation. And we would like to address this and measure with the Electron-Ion Collider. Another cool thing that I showed you this one-dimensional plot of the distribution of the quarks inside the proton, but we would like to see the three-dimensional image of the proton. We would like to see how they are actually distributed, not in terms of this longitudinal position of the X, but also in the transverse plane. And I have a cool video for you. Maybe I will just, due to lack of the time, I will going to skip. But this was done by the arts at the MIT group in a collaboration with the Jefferson Lab, and that was really great way of artistic view of the proton structures inside, and that gives you the feeling what we are measuring, and why the various parameters of X and the Q squares are really important. So let me start. So This is what I try to explain, that we would like to check with X. X, I would like to remind that this is the fraction of the momenta carried by the quark, and this is what we are probing. And this is how it looks when we are probing the tiny little piece. So the X is 0.001 of the proton momenta. And you can see this is made of like a soup of the gluons. If we go to the what we call the C quark regime, we started to see the quark antiquark pairs, which are popping up here and there. And when we go to the X of 0.3, which is 1/3 of the proton momenta, we're starting to see those 3 valence quarks and how they are interacting with each other. So this is exactly the cool image showing you how the different scale or different probe that we have. Another way of checking is the Q-square. So the Q-square is actually our resolution. As you can see that for the Q-square about 1, the resolution is very bad. That's why you can see the hyperpixelization. But as we go to the higher Q-square value, the resolution of the image is getting better and better and better. But during this sort of transformation, as you can see that the longitudinal profile of the proton is changing, so it's becoming as a pancake. That's why it's so difficult to measure the structure inside. And this is the valence quark distribution. You can see that the valence quarks, 3 valence quarks inside the proton. But as I told, like the higher it goes with the Q-square, more like pancake the protons becoming. And I also would like to show you how this distribution looks like when we look at the same graphs which I showed to you, how the resolution and this X plot are related together. So we can see that here we have the soup of gluons and then the valence quarks at the 1.3x region. So I hope you like this, and let's move on. So another question what we have to address with Electron-Ion Collider is how we understand the mass. So we know that the Higgs mechanism explains the mass of the quarks, and if we take all the mass, all the quarks inside the proton, so 3 valence quarks, so we will have a scale about 10 MeV. But if we measure the mass of the proton, it's almost 100 times larger than that. And this is a question like what is giving the protons this mass? Yeah, and as I would like to remind that the Higgs mechanics only explain 10 MeV out of the 1000 MeV of the proton mass. Another property is the proton spin. So we know that inside the protons, all the quarks are sort of spinning. And the quark contribution is only 30%. Gluon contribution is about 40%. But what is the rest? Yeah. So how we can measure and what is really contributing to the leftover contributions to the proton spin? This is a question which we would like to address. Another question is what we are doing with the extreme densities. Yeah. So and we know how the proton structure looks like, but what if the proton is inside of the like heavy ion, like I don't know, uranium or iron, and if the structure is modified, can the quarks inside the protons see the quarks inside the other protons or the neutrons? And what is how this color flow and if they are moving inside or not? Another question is confinement. Yeah, so we know that we discussed it that we cannot see the quarks as a standalone species. They all forming hadrons, and the question is how they are forming this. Is it happening inside of the proton or outside, or what is the mechanism of the hadronization, let's call it, producing the other particles out of the quarks is happening. So this is what we also would like to address. And the coolest thing, and this is my favorite topic, what is up to now, I explained you everything, what is the standard model, predictions, and what described in the standard model. But it could happen that some new particles could emerge when you collide the electron with the quarks. And this is one of the predictions from one of the theoreticians about the leptoquark or leptogluon new particles. But for that, we need to have really high center of mass energies and a lot of data in order to observe. So let me introduce you to the Electron-Ion Collider, and this is advanced accelerator which will be built at Brookhaven National Lab in partnership with Jefferson Lab. And we are going to reuse or upgrade the existing hadron complex, which is currently operating at the BNL, which called RIC. You can see the picture of the tunnel. This collider can accelerate protons and ions, so protons up to 275 GeV, and they already have the tunnels, infrastructure, everything. And what for the EIC, we need to build the electron ring. Yeah, so this will be brand new. So we are going to reuse the same tunnel, but add another ring for the electrons. And, I collided at what we call the 6 p.m., 6 o'clock regions where the detectors will be installed. And of course, we need, so you can see, by the way, here, all the energies for the electron and the protons and the center of mass energies. And we will have the polarized beams, and we'll operate with the protons and with the ion species. And of course, we need a good forward instrumentation. This is really important for the imaging program for of the EIC. A few words about accelerator. Of course, we will use the state-of-art magnets, either superconducting or conventional magnets. So we need to have them in a ring in order to deliver the beam to the interaction region. We will have state-of-art radio frequency cavities, which will also, we need to accelerate the particles, and of course, the vacuum system, because all the particles inside the accelerator inside the very, very high vacuum. So this is sort of the goal. If you look at the landscape of the DS facility, and DS is deep inelastic scattering, E plus E minus, electron-proton colliders, you can see that this is a CBUF. It will have a lot of luminosity, means a very high data rate of the collisions, and this is the future and proposed colliders at CERN. And EIC is sort of sitting somewhere in the middle if you look at the energies and the like data rate plot. So they will have, I mentioned that we will have polarized beams and nuclear beams, and this will be really the first in the world polarized electron-proton, electron-ion collider. Let's look at the experimental setup. So I mentioned that it will happen at the 6 o'clock region. here in this region, the electrons and the protons will sort of hit each other, and we will have the detectors around them. So we need to detect everything what is emerged out of those collisions, and we have to cover 4 pi area, so that there is no escape for any of the particles. We need to detect them all. So this is the location of the potential location of the Electron-Ion Collider detector. The central part, as you can see here, is about 9 meters. We will have the crossing angle, so the beam will have the crossing angles. That will allow us to place some detectors along the beam lines. And those forward and backward detectors are really stretched and distributed along the beam line. So like plus minus 40 meters along the beam line. And it's really important for us to make sure that this design can operate with a different beam energies, with a high rate, and of course, the integration of this accelerator is really important. And this, you can see how the detectors looks inside the hole. So we need to make sure, because we are reusing the infrastructure which is currently available, we would like to make sure that this detector is sitting and can, we can place it inside the hole, and we can slide it in and out for maintenance and so on. So I mentioned earlier that we have about 200 particles, and we want to detect them actually for all the particles which we measure. We would like to measure their momentum or trajectory. We would like to measure the charge, origination or vertex, energy, and type of the particle, which is mass. But we are really fortunate that we do not have to really detect all 200 particles, because only all of them are decaying. So they all decay into the other more stable particles. And if you look at the lifetime or decay lengths of various particles, so only 13 particles can really fly the distance, which is more than 500 microns. And I just would like to remind you that the thickness of our hair is about, 50 to 100 micron. So that means after the 100 microns, flying the 100 micron thickness of our hair, most of the particles will decay and only 13 will remain. And this makes, of course, the life much easier, because we only have to focus on the detection of those 13 particles. So this is how the central detectors looks like. It has a layered structure. It has a vertex inside to measure the trajectory. It has the particle identification to sort of distinguish between various species. It has the electromagnetic calorimeter and hadronic calorimeter to measure the energy of the electrons and the hadrons. And of course, we have the instrumentation along the beam lines. So let's look at the short video how this looks like in a 3D. I know that you like the 3D motion. So this is how, with respect to the size of the human, these detectors looks like. And this is what will happen during the collision. So electrons and the protons will collide, and they will create some clusters in the detector, and we have to analyze this and make sure that we capture and can analyze actually everything. As I mentioned, there's different detectors which are measuring the trajectory or the energy of those emerged particles, and this is what how that looks in a 3D view. And another view, you can see this is the beam elements which are delivering the beam to the interaction region. You probably cannot see really all 40 meters away, but this is just a central detector and a lot of electronics racks around this. And this is just for you the size of the person staying nearby. So let's briefly look at what kind of detectors. So as I mentioned, that particles have to interact with the detector material, and they have to. That's why we are measuring the particle momenta using the magnetic field, which is solenoid. When you know this famous formula of relationship of the magnetic field and particle momenta, they we can also measure the bending radius, and depending if the particles go to the right and the left, we can measure the charge. And we know that this momentum measurements, if you look at the resolution, it has a linear dependence on what kind of momentum this particle has. So that means we need to really build high precision detectors in order to improve the resolution, especially when we are talking high momentum particles. So this is the solenoid. You can see it has the bore of almost 3 meters and operating at 2 Tesla. And inside, I probably will skip the slide. So, and inside we have the tracking detectors, which have really fine granularity. And we have to place them very close to the beam pipe in order to be able to reconstruct the vertex. This is exactly what I explained to you. So this is when the particles, like D+ is one of the example of the short-lived particles. When it's produced at the interaction region, it flies about 100 microns, and it decays to the pions and the kaons. And we are detecting those products, and we plot the invariant mass in order to sort of prove that it was this or other particle produced. As you can see, we cannot really place the detectors very close to the interaction region because we have to deliver the beam. And that's why we have to rely on good algorithms for the track reconstruction in order to sort of be able to identify if those pions and kaons were emerged from the secondary vertex or from the primary. And this is exactly where the silicon detectors are playing the key roles. And you can see the granularity of the pixels about 10 microns. And we have to cover the really huge areas with this technology. So I'm showing you one of the concepts which we are right now exploring, similar to what our CERN collaborators are doing at ALICE. It will be fully curved layers of the silicon detectors with very fine granularity. And in order, as you know, the silicon detectors are really expensive, so we need to make sure that we have we cover large areas. That's why we have the silicon detectors very close to the beam pipes, and as we go out, we use the more less robust technologies, and this is like micro pattern gas detectors, so that they have really good also granularity, about 100 microns. But still, this is a bit cheaper technology compared to the silicon. Also, is the curved, and we have the disk structure for the end caps. So I do not have a time to really deep into the development, but I want to also mention how we measure the energy. So we know already so tracking detectors provide the measurements of the momentum, charge, and the vertex. But in order to measure the energy, we have to completely stop the particle and absorb the energy of this particle. That's why the colorimetry is the outermost detector. So the measurements of the energy is destructive. So we have to stop all the particles. And after the colorimeter detectors, colorimeters, the particle is not really existing. Yeah, with few exceptions of the muons and neutrinos, which are penetrating through the material, and for that purpose, colorimeter is the outermost detector. And they can measure both charge and the neutron. Tracking detectors only can measure charge detectors. We have two different types of the colorimeter, electromagnetic and hadronic colorimeter. As you can see, that the shower are completely different for the if you measure the electrons or if you measure hadrons, the particles which are made of the quarks. That's why we have a different instrumentary. So for the electromagnetic colorimeters, in one of the sections in the end cap, we are going to use the crystal colorimeter. And this is about, you can see the size, so the granularity is 2 by 2 by 20. The production of this crystal, growing those crystals, are really time expensive process. So we need to about 2 days to grow a single crystals. For CERN, it took 10 years. So that's why we are, for the Electron-Ion Collider, we are starting now. And this is really important to stay on track for that. And this is really cool technology, and up to now, I think the best resolution which you can get. And I'm probably skipping the other technology here just to have a time. So you will have, we will have also hadronic colorimeters. You can see it's really thick because we have to stop them particles completely. We have different technology like steel scintillators and so on. We would like to identify the jets, so that means we would like to have the structure of the hadrons inside the jet, being able to identify if it was a jet coming from the quark or from the gluon, or if it will have the decayed length, or if it was from tau, and what kind of particles there are inside. That's why we need really, really high granularity for that. And for particle identification, this is really interesting because we most of the particles we can just identify by looking at the topology inside the detectors. But for the individual hadrons like pions and the kaons, we need the specialized detectors. And there's several methods which you can use for the detecting of the type of the particles, and I will just focus on the time of flight and the Cherenkov detectors. For the time of flight, this is a technology based on, again, silicon. As you can see, they will have very, really fast timing response. And the technology, the principle of operation is the following, so that if the particles have the same momentum but a different mass, you will see the difference in the arrival time in the detector if you just place the two detectors apart. And for this technology, we have to really identify or measure the time in such a precision which is order of 30 picoseconds, just for you to understand the scale. So 1 picosecond is 10 to the minus 12 seconds. So it's 1 trillionth of the second. This is how fast those detectors are working. This is because we have to really distinguish between the different mass of the particles. And this is technology which nowadays are available. So I am not going to talk about the particle detectors. We do not have a time for this, but I have a slides for you that we also have rich detectors inside the EIC. And of course, we have the forward and the backward instrumentation. I want to focus a little bit on the luminosity. I have 2 minutes left, and this is really important to understand the collision rate of the particles. I didn't mention about how fast, how many particles we have in each of the collision, and I place it here. So we'll have in each bunch about 10 to the 11 particles, and they are colliding with a frequency of 10 nanoseconds. So. The measuring of the luminosity is really important because this is directly relates to the formula of how many events you want to you will detect. And I want to show this slides. This is a contribution from the York group. They are involved in the measurements of the luminosity detectors. You can see that the different colorimeters and fast tracking systems. And I want to really highlight here that contribution from the York University is really, really important. And of course, we have to analyze the data, we have to collect everything, and we have to analyze this. So we are using Giant4 to simulate the detectors. We are using, of course, all AI tools, which are nowadays are really popular. And this is what kind of tools we are using for analyzing. Another cool fact, what I wanted to show is what is the data flow coming from the detectors. And if you look at the volume of the data, you will be really, really surprised because we are writing on a storage with a rate of the 2 or 3 DVD movies per second. So it's really amazing. And but the technology nowadays allowing us to do that. And with that, I want to go to the collaboration. Right now, the EPI collaboration is formed. We have about 171 institutions from 23 countries. And the user group is even larger. So we have about like 1,500 scientists all around the world. And it's actually, this is a huge project and we cannot really build it with a single country. We need to, all of you and all countries contributing in order to realize this project. And this brings me to the schedule. So we have a design phase. We are at design phase now. We will start the construction about in a couple of years from now, and the start of the operation will be in 2034, 2035. And this is what I want to conclude with this. So I showed you the goal, I showed you the science questions which we would like to address, and the EIC is really depends on motivation of the young people, and looking at the time slot, this is Collider for you guys. So thank you very much. And with this, I want to stop.
Thank you. Thank you very much, Julia, for that.
I hope I stayed on time. So.
It was perfect. I appreciate that very, very much. One question I did have for you, Yulia, was back when I was a student, before even the relativistic heavy ion collider was formed, I worked at Brookhaven Labs building a big particle detector for use at Brookhaven Labs. Are there roles still for students, undergraduate students and others, to work on the installation of detectors do you envision as this moves to construction? Or is it entirely handled by technical professionals and engineers these days?
So not at all. Of course, we rely on the students. We rely on our partners from the different universities. As I mentioned, we cannot really build these detectors at these scales just using the stuff available in either Brookhaven or Jefferson Lab. So we And we have to like distribute the load, and most of the work is done by like the checking the various, the subsystems. For example, I mentioned about this crystal colorimeter. So one of the tasks, for example, is that check the quality of each crystals, check the size, do the measurements, make sure that the everything is aligned together. And this is a really good project for the students to like help, because we have to measure, as you can see, like thousands of such crystals, and we have to rely on the people power to do this work. And some of the detector, as I mentioned, for example, this luminosity detector with York is currently contributing, is actually the tabletop detector, so really compact. It has like 20 by 20 centimeters. And but this is really important for the electron-ion collider, because we need to understand our luminosity. We need to understand what is the data rate, how the particles are sort of colliding, what frequency. And this is the contributions from the York group, and like 100% from the York group. So we are not really helping with that.
Mhm. Excellent, thank you. There is a question that came in about how can we apply the knowledge of subatomic particles to developing new technologies?
Oh,
Is
this
it?
is a really great question. So right now we are really addressing the fundamental question. So there is a lot of probably could be a lot of answers how you can apply this in the future, but at the moment we are addressing the fundamental questions. And later when we know how to handle, how to like manipulate the quarks inside the protons, this could be addressed more globally. But right now, I see it from my perspective that we are trying to address really like the fundamental questions, not really like the applied physics. But once we understand, once we know how to handle those tiny little pieces, we will pass it to the next level and apply this for the other fields. And another word I want to add that because particle physics, accelerator science is usually at the top technologies. Yeah, as I mentioned, that we are using the detectors which are like state of art, like picosecond resolution or micrometer resolution. And we are always pushing the technologies to the limit. Because of our goals, because we need this precision to do our fundamental studies, and this is what drives the technologies as well, right? So we are asking for the call for the detectors, and we see what is available on the market, and this is what drives the research and development in this field.
Excellent. To follow on, you mentioned that, of course, driving this project is the fundamental physics, our understanding. And you mentioned that the huge team of scientists. Do you think that the technical specialists and the engineers are about the same number-wise, or is it much larger in order to ensure the success of the project?
Of course, we rely on the engineering and the technical support. I cannot really see the scale right now, but of course we will rely on the designers who are like developing this in a CAD. We rely on different components in a CAD, right? We rely on the technicians who are going to build and put all the screws together for the design. So if we are talking about so this what the numbers of the scientists which I put here, it's really like the scientists, right? But the entire team is much larger.
Excellent, thanks. There's also a question that would like to explore more about by what it means to go beyond the standard model there was particular interest in leptoquarks that you had
Oh,
mentioned.
yes. Yeah, this is my favorite topic. Yes. Let me go back. Yeah, so this is the beyond the standard model. Of course, we have a lot of theories which are trying to see what is not yet described in a theory, right? So standard model describe the quarks, they describe this table which I showed of the elementary particles. But what is beyond that, right? And one of the ideas was that the electrons and the quarks, as I show you in this picture of this table, they are fermions. They are pretty much the same, right? And they have the half spin. They have 3 generations. They have a hierarchy in mass. And there was the idea like why it couldn't be the same particles, or why the quarks, like U quark, can let's say transform to the electron, for example, right? Why they cannot really, leptons cannot be transformed to the quarks, and the quark cannot be transformed to the leptons. And some theory shows that in principle they can. This is what they call the beyond the standard model physics, when the electrons and can like be transformed to the quarks, and by exchanging another carrier, a force carrier, which calls leptoquark. I don't know if I explained it in details or not. But this is beyond the standard model, right? So this is what we are like the same as like string theory, yeah. So we or supersymmetric particles. So we know that there's a theory which predicts that, but we haven't observed them yet. So we are setting limits. We are trying to match. For example, there was possibility to search for this leptoquark is by looking at the EIC at the like the tau production, yeah. So you measure, instead of the scattered electron, you measure tau, and this gives you a direct hint that there's something happened, that there's we had the electron in the initial state, and we do not have the electrons in the final state. That means something is wrong. So we have tau. That means something happened here in between.
Excellent. Well, thank you very, very much. And so certainly this is a very exciting project. It'll be the premier discovery facility when it's up and running. And certainly my hope, as well as yours, you had expressed, is that some of the audience now listening to us will be at the start of a scientific career or an engineering career, and that could contribute greatly at the right moment when this exciting opportunity is now running. So this is fantastic. I would like to thank you on behalf.
As I mentioned, that this is technology for this accelerator facilities for the next generation, and we really rely on the like smart and motivated young people, and there is a lot of opportunities at the EAC which one can contribute, starting from the engineering and like designing to the real construction and like simulation and analyzing results. And thank you all for having me.
And thank you very much for your presentation this evening about this exciting opportunity and all these science questions. What I'd like to remind everybody is that the recording for this event will be available on the Nuclear Masterclass website next week, and there's a link that will be emailed to all of us as ticket holders. Next week's webinar will be the final webinar. We'll be exploring how lasers can be used in nuclear physics research, and we hope to see many of you there and then. So thank you for joining us this evening, and I would like to wish you all a very good evening.